So in the current video I will be discussing the drunk passenger problem, which is a very famous problem. I have also personally encountered this problem in one of my interviews. So let's go through this. It is a very popular problem. There are several variants of it which can appear as follow-ups. So I will first discuss the central problem. I will try to keep the treatment more formal and not assume any constants until and unless necessary. So let me specify the problem. The problem is that there are people rather 1, 2, 3 up to n, and they are standing in a line. So and here there is a plane, right, which they are supposed to board. The person named 1 is at the front of the line, so this is the front, and they all carry some tickets. The scenario is positioned such that the person 1 carries ticket number 1, person 2 carries ticket number 2, and so on. Nth passenger carries ticket number n. The problem is that the first person is drunk, right? So and the rest of the people, they are all sober, not drunk. So the problem is that as one is drunk, he might choose any seat in the plane from 1 to n. Any seat he can choose randomly, and then for all the further down the line, for all the sober people, if say we talk about 3, when the turn of 3 comes to sit in the plane, if seat number 3 is vacant, he will sit at his own seat, which is seat number 3. But if seat number 3 is full, he will again choose any seat randomly and just go ahead and sit there. So this is the scenario. So basically 1 is drunk and all others are sober, and if sober, they choose their own numbered seat. Now the problem is the standard problem, the first variant rather, let us say. So this is our variant 1, is where we have to see what is the probability that the nth person, right, nth person, which is capital N, let's say, that is the last person, this person, sits, nth person sits at his own seat at, say, seat number n. And this is a problem which, when I first personally encountered it, I wasn't able to solve. There are 2 different ways to solve the problem. One method is just recursive, and this is highly mathematical. I will go through this as well, but the central emphasis, and I think the one which we should have some intuition of, is intuitive one. And this is just by clever design of events. And often people think that events are something which are not too useful, just for bookkeeping terms, but this problem, I think, shows that events are very, very important, and how you define events and probability it can basically change the nature of the problem, and it is not appreciated enough. Mostly textbooks ignore this part of how to design events, but I think this problem is a great example where a clever design would significantly ease the problem. So let us, as I have laid the foundation for it, let us first go for the intuitive solution, and then, just for reference of how to rigorously mathematically go through it, I will maybe present the recursive solution as well, if time permits. So let's see. um, the intuitive way to think of it, as I said, is mainly through design. So say we choose two events, E1, and this is the event, let's say, and the second event is E2. Now this is a problem where once you see the events, it would be very very easy um, to see the follow-up of how the problem would proceed. But the designing of such events, it is the crucial thing which would differentiate whether you get the problem or not. And I think this design will only come through practice and only through several examples. And basically it has been proved as well that human mind recognizes patterns, and if you remember this pattern, it is super useful. So I would just go ahead and maybe in this particular case, list what those events are. The first event is, say, seat number one is occupied before seat number n, right? And E2 is seat number n is occupied before seat number 1. And the interesting thing is that these two are exhaustive, as there is no other case. So either event 1 happens or event 2 happens. Either 1 is occupied before n or n is occupied before 1. There could be nothing else. E2 is basically even complement. So the first point is that they are exhaustive and of course mutually exclusive. They cannot happen together as well, right? These are just for naming purposes. I am just trying to make the proof rigorous, nothing else. So it is exhaustive and mutually exclusive. But how do we go ahead and inspect? So see, the benefit here is that what if seat number 1 is occupied before seat number n? So I always love drawing placeholders like this just for clarity. So say 1 is see, there are several cases. Say the drunk passenger, the one carrying token number 1, does actually go to his original seat, right? Then all the ones who are coming after him, they will all get to their designated seats because they are all sober. So and this qualifies as E1 event, right? This is our event E1. I hope this is visible, the blue color. Then there is a second case. Let's say this one person, this goes somewhere arbitrarily, but not at the end, right? Not here, but he might go and not there as well, because that is something we have already discussed above. But he might go here, and so on, everywhere. Out of these possibilities, say he goes somewhere, then what happens? Then all the people who are in this region, they all will get their correct positions, right? Because those seats are already vacant. But when one has occupied this seat, now a new passenger comes up. Say this was the kth seat, then the passenger number k, he would face a difficulty. Now he would have to choose a seat out of 1 to anything except the ones which have been correctly occupied. He can choose any of the except this, he can choose any of the positions at random. Again, if he chooses 1, what happens? We again go to E1, that is seat number 1 is occupied before seat number n is occupied. And if he chooses any other seat, say he again chooses this, so what happens then? This person becomes the new drunk passenger in a way. Now he has to choose from 1 to this range. So basically there is a transfer of drunk passenger taking place, right? So yeah, these are all under event E1 case. What is the E2 case? E2 case is simply that maybe the first passenger itself, he goes to the nth position, or one of the intermediate drunk passengers, they go to the nth position. Now let us go further, and this is the crux of the argument. This was the present discussion. It was just to make sure that you understand the two cases. And now, okay, there should be some way to increase it, maybe. Yes, there is. Oh no, what did increase? Oh no, oh, sorry, I changed something else. Okay, I don't think there is a way. It's not a sprint. So now we will see what happens for E1 and E2. Now if E1 happens before, if E1 happens and E2 does not happen, right? Okay, let me, if E1 happens and E2 doesn't happen. So if E1 happens, then person number n, what happens? He sits on his own seat. Right, and if event E2 happens, then n does not sit on his own seat. So once this gets established, we just need the probability of E1. So our answer, in a way, is simply probability of E1. And here comes an interesting case, an interesting thing as to how you would find out probability of E1. What is the probability that seat number 1 is occupied before seat number n? Because we see that these are mutually exclusive and exhaustive, so one of these has to happen. And if E1 happens, we can be sure that seat number n is vacant and the nth person would get to his own seat. So that is a favorable event. And if E2 happens, that is, if 1 is vacant and all the remaining 99 seats are filled up when we move on to passenger 100, say, if n is 100 for example, then we can be sure that this is an event which is against us. We are not going to sit at our own location. So we just need the probability of E1. And here an interesting, very very interesting similarity argument comes up. And we will see that this argument is extremely important, the symmetry argument, because in the further variants of the problem as well, we essentially would be using the same symmetry argument. So what is the probability of E1? So the claim here, which is based on symmetry, which is the one we make, is that and this is something really important, we are claiming that probability of E1 is simply equal to probability of E2. That the probability that seat number 1 is occupied before seat number n is the same as the probability that seat number n is occupied before seat number 1. This requires some verbal description if I am talking to you, and if the mathematical proof is not rigorous, which in intuitive solution it is not. So what can we say? See, seats basically are just numbers. So the probability, what is the probability that the first person, then the first seat is occupied before seat number n? It is just a matter of convention. We can see the point which I want to bring forth is that if you have claimed that this is our seat number 1 and seat number n, would the problem change if, say, you have labeled them like this, n minus 2, just for completion, n minus 1? Would the problem change in any way if I label this n, if I label this seat n minus 1, if I label this seat n minus 2, if I label this seat n minus 3, or if I label this seat 3, or if I label this seat 2, or if I label this seat 1? These are two different labels. Say this is our labeling 1 of the seat and labeling 2 of the seat. The thing is that we have to think whether these are fundamentally different. Is there some case where L1 happens where L2 cannot happen? And the claim is that these two things are exactly identical, because see, when the first person himself is drunk, what happens? He can choose either 1 or n. So he might choose this seat or he might choose this seat. This is purely random. Both of them are 50% likely, right, to happen. Uh, Not exactly 1 upon n likely to happen, but that is basically equal, because they are both the probability that the person chooses 1 is 1 over n, and the person chooses n is also 1 over n. So there is no fundamental difference between them. Now 2, if you are making 2 sit here, why not make 2 sit here? As per this labeling, what is the issue? There is no difference. You just flip the labels and the problem is exactly identical, right? So now we see that what is even? Even is just the seat number 1 being occupied before seat number n. That is, and see, L1 and L2 are not fundamentally different. This is what we choose to be our labels. There is nothing inherently different in them. So E1 is just under L1, right? That seat number 1. And if we consider E2 under L2 labeling, that seat number n is occupied before seat number 1 in this labeling, that this is occupied before this, okay? And as per E1, 1 is occupied before n. What is the difference? In both nothing, because in both the cases we are claiming that these seats basically are being taken before this seat. So we do not know exactly what it is, equal to what. This is something we don't really know. But what we know is that they are equal, number 1, and number 2, that they are exhaustive. That means that their sum being exhaustive, their sum, it has to be 1, because one of them has to happen and only one of them can happen. There is no intersection. So their sum is 1, they are both equal, hence we can claim that they are both 0.5. So there is a 50% likelihood that the nth person would sit at his own seat. This is the first variant of the problem, right? I hope you got it. If some more clarifications are needed, you can let me know, and I will provide it in a further video. But the symmetry argument is quite subtle according to me, in my opinion, and it is, for the first time, it was not intuitive to me, but as I said, it has been asked in at least 2 interviews in which I have personally appeared in. So it is an important variant of this problem. But again, this problem is centrally from Xinfeng Zhao, but a very popular problem in general, which is practiced by a lot of people. So now I will go ahead and we will discuss the variant 2 of the problem, and that involves some even beautiful logic argument, you will see. Okay, so the cursor speed when you do this becomes slow. Fine. The second variant of the problem is even more interesting, but again, a beautiful choice of events makes the problem very, very easy. So, while erasing, which is quite time consuming, let us say I tell you the problem. The problem is that again we are in the same scenario. We are being asked that the kth person from the end, let's say, how likely is he going to get his own seat? Let me draw the scenario once. Yeah. Oh, okay, I will have to erase this as well. This is too time consuming. Would have to figure out some way, some selection or something which would make this process faster. Figure it out later. So the problem is that again you are given n positions, right? 1 to n. We are being asked that what is the probability that the kth person from the end, so this is the first person from the end, this is the second person from the end. We already know that this person has 1 by 2 likelihood of sitting at his own seat number. This person, what is the probability that he sits on his seat number? What is the probability that the third person sits on his designated seat from the end, and so on? What is the probability that the kth person sits at his designated seat? Is it all half or something else? This is the question. Of course, this case k equals to 1, in the final answer when we put k equals to 1 we must get half based on what we have just done a few moments ago. So this is the problem. Let us try and solve it. Again, a clever design of events would make this problem fairly simple, and I would maybe demonstrate that. Here what we will do is, let me show you 1 minute, give me some time. This is an interesting problem because for the kth person we will design multiple events. E1 is the event that first seat number 1 before let us say k plus 1 and so on up till n, that seat number 1 is occupied before all those seats. Similarly, let us say label it k, is number k gets filled up before 1 and so on up to n, 1 comma k plus 1 and then continuously up to n. Similarly, say e k plus 1 is number k plus 1 is filled before 1, then k plus 2 and so on up to n. So do you now see a pattern in the way we are designing our events? This will go up to en. You will see a pattern in designing our events. When we are talking about the kth person, what we are interested in is that which of the seats gets filled first, whether it is 1, k plus 1 and so on up to n, which one of these gets filled first. That is the problem we are interested in. In the previous case, when we had 1 and we were interested in whether the nth person would get his seat or not, we were interested in which of these two fills first. You can sort of link this variant to the previous variant. Earlier, there in that problem, we were interested in which one gets filled first, whether the first seat or the nth seat. Here, we are interested in if we are talking about the kth person getting a seat from the end, we are interested in which seat will get filled first, 1k, k plus 1, or up to n. Notice that we do not really care about seats 2 to k minus 1. We are not worried about them. Just like in the previous case when we were talking about nth person, we were not concerned about 2 to n minus 1. So there are parallels, right? The way you design, and it is essentially the same. So we can say that the variant 1 is just a subset of variant 2. So this is our variant 2 problem, and this was our variant 1 problem. If you understand variant 2, you will get the answer to variant 1. It's just for k equals to 1. But still, we did variant 1 before variant 2, so that we have some intuition as to how these events are being designed. But now you see, we design events in this way, that we first say for each of the seats, and 1 to k plus 1 and so on up to n, we see which of those gets filled first before the others, right? And we make events based on that. Now we will consider how is this design of events useful. I mean, 1 for k equals to 1, you already saw it, how is it useful in the variant 1 case. But here we will go into the k equals to some number, nth say case, and we will look at how that is useful, how this design helps us. So one thing you can see is that, again, from just basic maths, all these events from E1 to EK, E1, EK plus 1, so on up to En, they are again exhaustive, right? One of them has to occur, right? By the very definition, you can say why we are saying 1 before this, and why not seat number 1 is filled first, because, well, that is not exhaustive, because then you will have to consider, so say why not consider E1 is seat number 1 gets filled first, then E2 seat number 2 gets filled first, then E3 seat number 3 gets filled first. That is an obvious question to ask, but that is not a good way, because number 1, the cases are not very useful, and number 2, to make the set exhaustive, you will have to consider E2, E3 and so on, and here we can go ahead with just 1, k plus 1 and n, and we see this is all which matters. We do not really care about at what position 2 gets filled, and just by construction, that saying before, this keyword is so important in designing the events, that you will see that they automatically become exhaustive, because one of the seat numbers present in the set must get filled before everything else, right? So it is exhaustive by design. So, and further, they are again mutually exclusive. Any two of them cannot happen together, let alone 3 of them, right? So they are mutually exclusive, exhaustive. Again, that simply means that their sum, right? I am just using sigma notation so that I can write faster, because I am using a mouse. So the basic idea is that their sum, it has to, I is basically when you take 1, k and so on up to n, this sum is 1, because there are no intersections. This is just the principle of inclusion and exclusion we are using here, because there are no intersections. between any two events. Basically, EI intersection EJ is phi, which is the definition for exhaustive events. So basically we say that this holds, and now I will get to the interesting part of it, the final solution, right? And I need all these things, but not this, maybe, because this is just the definition of mutually exclusive. Yes, so now we come to the final part of it, and that is very, very interestingly, you see, if number one is filled, if number one is filled before everything else, then what happens? Let us consider E1. So all these from K, starting K all the way up to N, all these seats are vacant and one has been filled. So what does this mean? Well, all these, here we might have a random permutation from 1 to K minus 1. We don't really care. Maybe 1 is not here, maybe 1 was here, maybe 2 is sitting, maybe 2 is here, 3 is here, and the fourth guy is sitting there. I don't care. All I care about is that number 1 has been filled before K, K plus 1 and so on up to N. Then what happens? This is favorable for us, right? K will get to his own designated seat. What happens for E, K plus 1? Let us inspect that, right? This is really interesting now, because you will see that all but one cases are good enough for K to sit on his designated seat, right? So consider like K plus 1. What does this mean? This means that K plus 1 is filled before 1 is. So 1 is vacant, 2 is filled, 3 is filled, 4 is filled, 5 is filled, and K plus 1, say this was K. K plus 1 is filled before K has been filled. So what does this mean? How could this case happen? This can only happen if 1 sits here, right? Because if 1 sits at any other position, K should have been filled. Or maybe 1, not 1, maybe 1 sits here and maybe then 2 sits there, right? But something must have happened that K is still vacant. So when the thing comes to K, and K plus 1 has been filled before all others, we see that K must have been vacant. K must be vacant. Then only can K plus 1 be filled before, right? Because one of them, they have to drop back, and then the one, when one goes to some position, the passenger there maybe has went to some other position, and the passenger there maybe went there, but we do not care what the sequence of operations were. We just care about the fact that the K plus 1th position is filled and 1th position is not filled, Kth position is not filled, and so on. So in this case, would the person K get to his own location? Again, yes, because his seat is vacant. Similarly, because K plus 1 was no different than any other person sitting there further down the line, we can be sure that even EK plus 1 and so on up till En are all favorable. In all the cases, the kth person would sit at his designated seat, right? Because his seat would be vacant till that point of time, because once some drunk passenger goes to the place of K plus 1, it automatically means that everything before it must be set, right? K is vacant, so everybody, say one went to here, then this person went there, So everything in between, they must all follow whatever the convention was, right? Because one went to some other position, then the remaining all before it are unharmed, then this guy went to some other position, then all between it is unharmed. And we see that for all k plus 1 to n case in our E definition, they all must have went to some further position and k is still vacant. So in the kth position, we are safe. Definitely we can be sure that k will be sitting there, as between two drunks everybody is safe, right? Yes. So now we will see how to use this information. Of course, one more thing, that if the only red case is ek, when k is filled before everything else, and of course in this case you won't get to so k won't be able to sit at his designated seat because it is already occupied. So we see that one case is against us, and all the k minus 1 cases or whatever, how many cases are there? Yeah, k plus one minute, let me erase this. Yes, so basically what we see is that only one case goes against us, and all the remaining cases are in our favor. So what is the probability that k gets to sit on his designated seat? Well, how many total number of cases are there? So from k all the way up to n, there are n minus k plus 1 cases, and even is n minus k plus 2 cases. And how many of those are favorable? Okay, but wait a minute, sorry, I missed the part of the argument here. Are they all equally likely? That is the case we need to think about next. So let's think about it this way. We can be sure so just to bring forth the argument, we can be sure that these are symmetric once again, because when one goes to some location, the person at that location, he might randomly move to any other location of his choice, right? So okay, what I have done actually, I see, is that I have changed the variant slightly. I should have named these. Nothing has changed basically, let's stick to this, but this is like the problem now has became kth person from front, kth from front. The way I have labeled this has become kth person from the front. I should have labeled it this way, just a labeling thing, and this is just to make the final formula we get more succinct, you can say, nothing else, purely ornamental. Yeah, so where we were, I was claiming that all these events, they are equally likely, just like we saw just by the symmetry arguments. You can again draw two lines and just swap, label one of them as 1 to n and other as n to 1. Let us define the events in a different manner, right? Basically just nothing but just defining it so that the last guy comes up as kth person from last. So that is what we wanted. So yes, so how many cases are there in all? You can see that there are cases E1 to EK, right? So there are k cases there, and there is an En. So there are k plus 1 cases, and out of those, how many are favorable to us? So all except this case. All except this case. They are all favorable to us. So out of k plus 1 equally likely outcomes, k of them are favorable. So what is the probability that the kth person from the end sits at his own location? Well, that is simply k upon k plus 1. Now, in one of the online assessments I was given, so the time given for this problem was extremely low. So they were actually expecting you to remember this from off the top of your head, because then only you can solve this problem in such a limited amount of time. So you can remember the result, but just in case you forget, the reasoning behind, the logic behind this variant is this, the underlying logic, right? Of course we had messed up with the labelings, but that should now be rectified, that just from ek to en, if we count it from the back, there must have been k people, because we were talking about kth from the back. And this is extremely crucial, because if in the problem you are asked kth from the front, it is basically n minus k plus 1th or some other variant of this from the back, and you have to just calculate this quickly, and instead of k you have to put n minus k plus 1 both here and here, and you will arrive at the same result. So that is a small tricky part which you might see in a problem. Okay, so k over k plus 1, this pretty much ends our variant 2. There is a certain other variant which was asked in one of the interviews to me, but it was just to check whether you have understood the concept firmly or not, or whether you have memorized the result, which by the way you should, because this is a common problem. So k upon k plus 1 is something you should have on the top of your head, because if the time is limited, you want to answer questions quickly. A third variant is very, very interesting. Now we were discussing kth person from the back. That means we have already discussed kth person from the front, because we always know that a person who is k from the front, how much far behind is from the back, and you can just use the same formula. The third variant is, what if the first passenger was not drunk and some other passenger was drunk? And that is pretty much the final case we have in this interesting set of problems. I know the video has run long enough, but this is how I love to approach problems. I want to spend time with them to analyze all their possible variants. So now the case is that, what if dth person, what if this person, dth person was drunk? Now how do you approach the problem? Well, if you are observant enough, you will see that this is just the same problem with these many number of people ignored, right? You can see that you have just ignored these people. Why? Because if it was 1, he will sit here because he is sober. If it was 2, he will sit here. If he is 3, he will sit here. The dth person is the first person who is drunk, so he becomes the person labeled 1 in our previous case. and the problem resumes with the our n gets the value n minus d minus 1, because these d minus 1 people, they are all sober, they will get to their positions, and only the remaining people are the ones on which the problem has transferred. So again, the final person has a probability of half, this person has a probability of 2 by 3, this person has a probability of 3 by 4, and so on and so forth. The problem has not changed at all. It is, you can see that the probability is k dependent, it is k upon k plus 1, right? It is no n appearing here. So would the probability that he sits at his own location change? No, it won't, because it depends on k, not on n. So everything is unchanged. Everything is unchanged, right? The order is unchanged, and the order is really beautiful: 1 2 2 3 3 4 and so on, k and k plus 1. Okay, so that's it. I think I have discussed all the variants of this very important problem, and you may leave your feedbacks if you want in the comments, and that should be it. Let me end it here. Yes, and I will be coming up with more problems. If there are easy problems, I would maybe club many of them together in a single video. If they are deserving of a more detailed attention, like the problem we had here, I will go into its gory details and we will see. Okay, so that is pretty much it. Let me end the video